Why is the James Webb Space Telescope so powerful? What's the physics behind its capabilities? Today we go deeper, from redshift to orbital mechanics, and break down exactly why JWST will see where no telescope has seen before. I'm Ben, this is Physics or Bust. The first reason? Infrared vision. JWST doesn't just see in the visual, like the Hubble. It sees infrared, and that's definitely by design. But why does JWST need to see in infrared? I'll tell you. When light travels across expanding space, it stretches, a phenomenon called cosmological redshift. Galaxies emit light in ultraviolet and visible light. But for the really distant galaxies, by the time the light actually reaches us, it's been stretched into the infrared range. In physics terms, we're talking about Doppler shift on a cosmic scale. And JWST has been designed to catch those photons that have shifted out of the visible range into the infrared. Now, when talking about redshift, Z is the wavelength observed minus the wavelength emitted, that quantity divided by the wavelength emitted. JWST is optimized to detect light where Z is greater than 6, which means it's looking at objects that are less than 1 billion years from the Big Bang. It's using near and mid-infrared detectors that respond to photons with wavelengths of about 0.6 to 28 microns. This makes JWST a time machine, in a way, because it can detect the redshifted history of the universe. Here's the catch. Infrared light is emitted by warm objects, and warm in space terms is quite cold. We'll look more into the physics of this next, but first, if you like this video, you'd probably like this book. I've got a link in the description below. I do get a small commission, but it wouldn't cost you any extra. The principle of blackbody radiation is that any object that's warmer than absolute zero emits thermal radiation, even the telescope itself. JWST was designed to detect photons from extremely faint sources, so even a small amount of thermal contamination can really affect the signals. That's why JWST is passively cooled to around 40 Kelvin, and its mid-infrared MIRI instrument is actively cooled to 7 degrees using a cryocooler. The telescope has to be this cool because the blackbody radiation that would come off of it if it's above that temperature would just blind itself. The 5-layer sun shield blocks heat from the sun and Earth, allowing JWST to be the coolest telescope ever flown, in both meanings of the word. Next, we'll look at the orbital mechanics that sets JWST apart from most other telescopes. Unlike Hubble, which orbits the Earth, JWST orbits the Sun at the Earth-Sun Lagrange point 2, about 1.5 million kilometers further from the Sun than we are. At L2, the gravitational forces from the Sun and Earth combine to keep JWST in sync with Earth's orbit. So when Earth does one orbit around the Sun, so does JWST. Now, it's not parked directly at L2, but instead orbits at a halo orbit around L2, a stable path that prevents it from drifting away from L2. At L2, JWST can keep the Sun, Earth, and Moon all behind its shield at once. This is a manifestation of three-body orbital mechanics, where the gravitational potential allows for quasi-stable equilibrium points. And because L2 is always further away from the Sun than the Earth, the Sun is always on the backside of the shield. So JWST's instruments stay in constant shadow, which is crucial for thermal stability and long exposure times, making L2 the sweet spot gravitationally, where JWST can hover with minimal use of fuel and maximum observation time. Because in order to get images from the deepest parts of space, you have to do a really long exposure time because you're getting such a low intensity of light from those far reaches of the universe. To see ancient dim light, you need to collect as many photons as possible, which brings us to our next aspect of JWST, that big mirror. JWST has a 6.5 meter wide segmented mirror, nearly 3 times the diameter of Hubble's. That means over 6 times the light gathering power. But there's also a physics reason JWST had to have a large mirror. The resolution of a telescope is governed by the diffraction limit, which depends on the wavelength of light being looked at and the size of the mirror. Infrared has longer wavelengths than visible light, so to get sharp images, you need a larger mirror. JWST delivers exactly that. The collecting area is over 25 square meters, compared to Hubble's 4.5. Despite longer wavelengths, which makes it harder to resolve two lights that are really close to each other to get a clear image, JWST compensates with its huge mirror, meaning it can not only see further, but also see sharper, resolving the shapes and structures of galaxies formed only 1 billion years from the Big Bang. Now that mirror had to get into space somehow, and we don't have a rocket that can launch a 21-foot circular object. This caused quite a big problem in the design phase. JWST had to fold up in order to fit into its rocket. The mirror is made up of 18 hexagonal segments of gold-plated beryllium, chosen for low mass, high stiffness at cryogenic temperatures, and stable thermal expansion. Each segment is individually adjustable, using actuators to adjust tip, tilt, and piston motion to within nanometers. The sun shield, made of Kapton, a high-temperature resistant polymer, had to deploy to the size of a tennis court, and they all had to fold up to fit into the rocket, and unfold perfectly in order for the telescope to function properly. Only with cutting-edge material and deployment physics could we launch a 21-foot mirror within a 16-foot fairing. This wasn't just engineering, it was telescope origami. One mistake, and the whole mission could have failed. Thanks to all of this, the infrared sensitivity, the cold environment, the stable orbit, and the massive mirror, JWST isn't just taking pretty pictures. It's rewriting our understanding of the universe. It's revealing the first galaxies, only a few 100 million years after the Big Bang. It's capturing the atmospheres of exoplanets, looking for carbon dioxide, water vapor, and even methane. And with the amount of mass that JWST is revealing that we previously didn't know existed, some scientists believe that our need to have dark matter in our current theory will disappear the way of ether. JWST isn't just a telescope, it's a physics laboratory, flying 1.5 million kilometers from Earth. When you combine cosmological redshift, blackbody thermodynamics, orbital mechanics, diffraction optics, and some serious wizardry engineering, you get the James Webb Space Telescope. If you enjoyed the deep dive into physics, make sure to like and subscribe, and remember, keep asking questions. I'll see you on the next video.